Hello, here we continue looking at squares modulo prime, quadratic residues, and that corresponding Legendre symbol. So the main fact in this installment will be quadratic reciprocity. It is a deep result relating Legendre symbols for a pair of odd primes. Let's imagine two odd primes, and then P is better saying not in separate cases, but just Legendre symbol of P with respect to Q and Legendre symbol of Q with respect to P, very strongly correlated. Their product is a predictable number. It is -1, of course, to some power, and the power is P minus 1 times Q minus 1 over 4. So knowing P and Q, you will know the relation between these two symbols. Are they the same or are they negatives of each other? That's a very convenient statement for computing Legendre symbols, hence for answering these questions if some number is a square modulo prime. And to make this computation completely possible, let's review the Euler's formula for the Legendre symbol for -1. So Euler says that you just take the number and you compute its power p minus 1/2, and then you take the remainder modulo p, and that will be your Legendre symbol. Well, this number, -1, to any power will be plus or minus 1, so it will be already its remainder, will be its Legendre symbol. And that we can really see when it is 1 and when it is -1. So it is 1 if P has remainder 1 modulo 4 when divided by 4. The other case for an odd P odd prime is 3, remainder 3 modulo 4, and then the Legendre symbol of -1 is -1. So what it says is that for moduli which are prime moduli which are of the form 1 plus 4k, -1 is a square. And otherwise, when the modulus is a prime number of the form 3 plus 4k, -1 is not a square. So the last piece of information necessary for computation, that is just a consequence of Euler's theorem. That is a special case of it. This is not. This is just a result of a computation which will have to be done somewhere else. So right now I'm just collecting all the information. This is also going to be proved later, but I'm collecting all the ingredients which are necessary for computations. The exponent this time is p squared minus 1 over 8. And again we can spell it out, write the conditions for when it is 1 and -1 correspondingly. So here, in this case, P has to have remainder modulo 8 of the form 1 or -1, which is same as 7. The other two cases are 3 and 5 modulo 8, the remainders of an odd number, odd prime, and that will give us -1 for the Legendre symbol. So again, these are the answers to the question, is 2 a square modulo prime P? Well, it is if P is of the form 1 plus 8k or 7 plus 8k. And it is not a square if our prime is 3 plus 8k or 5 plus 8k. So now we are armed with the complete arsenal of tools to answer questions like that. Is, say, 2020 a square modulo, well, a prime like 1 or 3. So 103 is a prime because it's enough to check its divisibility by primes which are less than its square root. So up to 7 is good, and 7 doesn't divide it, right? If you take 70 out, you'll have 33 left. 33 is not divisible by 7. It is not divisible by 5, it is not divisible by 3 and by 2, obviously, so that must be a prime. And let's start computing the Legendre symbol in order to see the answer for this question. So the first move we can do is to reduce the actual number down to its remainder modulo 103. Its remainder or anything which we'll find convenient. So I will actually replace it not by its remainder but by negative version of it. So I can just take 20 copies of 103, and that will create 2060, and that will be too much, and then I'll have to compensate by subtracting 40. So I can replace the number, equally well I could have taken 63, and that would that would also be good, but I would just like to take 40 because it is smaller and it decomposes quicker into smaller numbers, which is a good computational move. So that is just using the periodicity of the Legendre symbol, the fact that it only depends on the remainder modulo this prime. So now we could use multiplicativity. We could write negative 40 as a product. It will be a product of negative 1 and then 2 cubed and then 5. So really I'm just factorizing down to primes, into a product of primes. And using multiplicativity of the symbol, I can write it as a product of 3. Well, I'm replacing the cube by the first power, so see that you agree with that. Because if a number differs by a square from another number, then their symbols are the same, so they are simultaneously squares or non-squares. So 2 cubed and 2 are simultaneously squares or non-squares. So it all comes down to 2. Right? If 2 is a square, then the cube will still be a square. If 2 is not, then the cube will not. So I could have really written an extra piece, an extra factor in the decomposition, which is 2 squared, but 2 squared is definitely square, so the symbol is 1. So now I'm looking at 3 instead of 1, but they are easier. The first one is just answerable by the formula, by the earliest formula. So we have to look at the prime and see if it is congruent to 1 and to 3 modulo 4, and 100 is divisible by 4, so the remainder is 3, so we are in the second case. The first symbol is negative. Then looking at 2, we have to now look at the remainder of 103 modulo 8. And this time you can take 80 out, so we'll have 23 left. 23 is 24 without 1, so it is 7 modulo 8. And in the, for such case, I should have the Legendre symbol positive 1. So now it is all down to the Legendre symbol of 5 modulo 103. Now I have 2 odd primes, and this time I'm going to use quadratic reciprocity. Quadratic reciprocity was observed by Euler already, but he couldn't really prove it. And the first proof was published by Gauss. And he published altogether a couple of dozen proofs, trying to find better and yet better, more revealing proof, because the question is, the statement is really bizarre. It says that 2 seemingly unrelated questions have correlated answers. So here you're asking about P being a square modulo Q, and now you're taking Q and looking at it modulo P. So the stories of things modulo Q and modulo P are really not so much related, and it is a miracle that we have a relation like that. So using this relation as a formula for this symbol in terms of the flipped version, in terms of the Legendre symbol of 103 modulo 5, I just need to see what is the sign which will make it true. And the sign is this sign, so I have to take 5 minus 1, which is 4, and multiply it by 103 minus 1, which is 102. They're both even, but the first one is divisible by 4, so when I divide by 4 I will end up with an even number, and so my symbol is just, my symbol here is just this flipped version. So now I just need to look at 103, which is as good as 3 modulo 5, and see if 3 is a square. Well, I can do it by listing all squares. 1, 2, 3, 4. Again, I need to compute only half of the list. So 1 and 4 are squares. 4 and 1 I will see in the mirror version of my little table. So 3 is not in the list of squares. 3 is a non-square. The symbol is -1. And so I have the last -1 in the product of 3 symbols. So the overall product is 1. And if that was my question to me, is 2020 square modulo 103, the answer is yes. So in the remaining part of this, let's look at why could we be interested in such a question, and yeah, maybe just going deeper and finding. So here we only have an answer that it is possible to write 2020 as a square modulo 103. So the congruence x squared congruent to 2020 modulo 103 is solvable. We can rewrite this as an equation, as a Diophantine equation. X squared is equal to 2020 plus y copies of 103. So now we have a parabola, a curve on the plane. So roughly it will look like that. It will be white parabola, of course symmetric with respect to the y-axis, dipping below the x-axis by about, if we divide 2020 by 103, it will be slightly below 20, right? So that is somewhere here, -20, somewhere here. And the question now is integer points on this parabola, integer solutions of this, which are as good as this. So we know that this parabola will have integer points, and moreover it will have infinitely many of them. So first of all, it will have 2 integer points with the coordinate in the range, with the coordinate for x in the range of 103. There will be this plus and minus solutions. But then we can shift the coordinate x and then effectively the coordinate y by copies of our coefficient here. So if we take, say, k copies and shift x by that amount, then when we substitute it in the equation, the square will become the square of the original x plus, I will write it as a product of 103 and everything else, so that will be 2k, right? And sorry, 2kx, and then k squared. So that is just using the binomial formula correctly. And then remembering that x squared was 2020 plus 103 copies of y, now we could see what is the effect on y which will compensate this shift. So y has to be shifted by this amount. So if we shift by 103 steps our x, we should shift y by, so k in this case will be 1, and then we'll have to shift by 1 plus 2 values of x. So it will be dependent on x, but nevertheless it will be possible to compute for any shift. So starting with the smallest values in absolute value for x, or the smallest absolute value for y, we can then, performing the shifts, see all the solutions. And in this case, you could, by trial and error, you could see the smallest value for y and the smallest value for x. So the smallest value for y will be negative 12, and for x will be plus and minus, because it's always symmetric, plus and minus 28. So let me call it the zero solution, or the first solution, but yeah, the first will be when I will perform a shift, and that will be with plus and minus. So that will be somewhere here. If this is say around negative 20, negative 12 is just below here, so negative 12, and then the 2 points we have here are to negative 28 and positive 28. So then, yeah, I could start shifting, and shifting in steps of 103, my x coordinate to the left and to the right. So if I just start with this point and shifting by one step to the right, one step of 103 will give me x1 minus. So that will be 103 without 28, and you could compute it to be 75. So yeah, this intercept is, yeah, what is this intercept? Is when y is 0, so that is just the square root of 2020. Yeah, it's, how to say, but 75 should be out of that. And yeah, so what is the square root of 2020? It's the square root of 2, maybe not, no, not this way. So if I take 10, yeah, no good. If I take 30, so 30 squared will be what? 300, no, sorry, 30 squared will be 900, so it will be below 1000. So I have to take more, I have to take, say, 40, so 40 squared will be 160, so it's still inside the parabola, so 75 is definitely outside here. I convinced myself that it should be outside. So negative 75, positive 75 are here. Then I need to compute the y node, or rather y1 with negative sign. So that would be taking y node, which is negative 12, and then we're just performing in one step. So case 1, have twice x, and x is x was negative 28, so twice 28 subtracted, and then there is something funny in here, so I've missed the multiple of 103, because 103 is supposed to be squared, so factoring one copy will leave me with another. So here I have 103 as the coefficient for k squared. So that since k squared is 1, because k is 1, I have 103 on top. And this is 56, negative 56, so together with this is negative 68, and subtracted from 103, it's like 43 without 8, so that is 35. So that is the elevation here for these 2 points. Not so symmetric, but yeah, this should be. So that is at the height 35. And then you could do the same shift by 103 to that point and see what happens, and you will end up with a point somewhere here. I will not do it, but the rest of the points can be accessed starting from here or from here by doing multiple shifts like that of 103 steps to the x-coordinate and recomputing what is the elevation using this. So again, that should be 103 copies of k squared. Well, that's one practical application of knowing if something is a square modular prime or not. That's it. See you later.